In this video, we're going to prove the weak law of large numbers. So given a random variable x, we have n copies of this random variable, and in this setup, they all have the same distribution and they are all independent of one another. And given this random variable, we know that it has a mean of mu and it also has a variance of sigma squared. We will define this new term called the sample mean, which is just the average of all these random variables. So you can imagine doing an experiment n times, getting n different results, and then taking the average. And then given this term that we've just defined, what the weak law states is that for any given value of epsilon, no matter how small epsilon we specify it to be, we can be sure that the sample mean will have a probability of 1 that it will be within a distance of epsilon away from mu. So essentially, since epsilon is arbitrary, we will have a probability of 1 that the sample mean will be within this distance away from mu. So we can make it arbitrarily close to mu with a probability of 1, as long as the number of trials tends to infinity. So what this tells us is that as long as we have enough trials for these random variables, if we have many trials, we can actually make the sample mean arbitrarily close to mu. And then we're going to prove this by using Chebyshev's inequality, which I've stated here, which we proved in the last video. And using this, we will be able to derive this statement. So in order to start our proof, we will start with the sample mean, which we derived previously, which is just the average of the n copies of the random variables that we have. And we need to apply Chebyshev's inequality to this term. So what we have to do, if we check this inequality that we established in our last video, we know that if we have a random variable, and in our case our random variable is the sample mean, we know that for it to deviate away from its mean by a value of k times its standard deviation, which is just the square root of its variance. So for it to deviate k times k standard deviations away from its mean, we know that this entire probability is bounded by 1 divided by k squared, where k is this arbitrary constant. And so in order to apply this statement, in order to apply Chebyshev's inequality to our proof, we need to find what the expected value of the sample mean is and what the variance of the sample mean is. So the first thing we're going to do is to find the expected value of the sample mean, and then the sample mean is just 1 over n times the sum of the n random variables. So we have this summation term over here, and then since this is an expected value, we can just pull the 1 over n term outside of the expected value term, and then for this expected value of the sum of these random variables, this is just the same as the expected value of the individual random variables summed. And then since we know that for each one of these random variables, they all have the same distribution, and so they all have the same mean, which is just mu. So here we essentially have n copies of mu, so we have n times mu. And then we divide this by n, so in the end, the expected value of the sample mean is just mu. So for this expression, we can already substitute in, for this term, we just have mu. And then now we have k times the standard deviation, so now let's just find the variance of the sample mean. And then we can take the square root of this term, and that will be the standard deviation of the sample mean. So the variance of the sample mean, this is just the variance of 1 over n times the sum of the random variables. And since a variance is essentially the square of how the random variable deviates away from its mean, every constant that you have inside this variance term gets squared. So if we want to pull this 1 over n term outside of the variance, we'll have 1 over n squared. And the inside will have variance of the sum of these random variables. But since we know that all these random variables are identically distributed and they're also independent of one another, we can break this variance term up into just the sum of the individual variances of all these random variables. And in case you don't know, if these random variables are not independent, then we'll also have extra covariance terms. But since in our case, they're all independent, the covariance terms will all be 0, so essentially we're just left with these terms over here. And similar to our previous step, this entire expression here, this is just n copies of the variance, which is just sigma squared, and then we divide this by n squared, so we have sigma squared divided by n. And so the standard deviation of the sample mean, this is just equal to sigma divided by the square root of n. And so going back to our original expression, this standard deviation, this will just be sigma divided by the square root of n, and then we will know that this is smaller than or equal to 1 over k squared. So the next thing we have to do is to specify what we want k to be. So in our case, k can be any arbitrary positive constant. So in our case, we will choose k to be equal to n divided by sigma, and then multiplied by epsilon, of the square root of n. So this is what we will specify our k to be. And then you'll see that we chose the reason why we chose k to be equal to this expression is because when we substitute everything in, we will just get back the statement that is the weak law of large numbers. So here you'll see that everything cancels out nicely. And then for the 1 over k squared term, we'll just have to take the reciprocal of this term and square it, which just gives us square root the square of sigma, and then we'll have n, and then this will also be divided by epsilon squared. And then the next step is to, let's just clean this expression up a bit. So essentially what we have now is that the probability that the sample mean deviates away from its mean by a value of epsilon, we know that this is bounded by sigma squared divided by n times epsilon squared. So this is what we know so far, and in order to get back the expression that we had for the weak law of large numbers, let's just clean this up a bit further. So let's just get rid of this. So I'm going to flip this sign by tacking on a negative sign to both sides, and then I'm going to add 1 to both sides. So what happens to this part is that if we have 1 minus a probability, essentially we have the probability of the reverse of this condition. So all we have to do is just flip the larger than or equal to sign, larger than or equal sign to a smaller sign. So we have this term is smaller than epsilon, and we know that this is larger than 1 minus sigma squared divided by n divided by epsilon squared. So now if we take the limit of both sides, so when n tends to infinity, so as n tends to infinity, we will see that this entire term will just tend to 0. So we have this probability essentially becoming larger than or equal to 1. But since a probability can only take on values no larger than 1, so if we have this term is larger than or equal to 1, essentially that's just the same thing as saying this term is equal to 1 as n tends to infinity. And so there we have it. This is the statement that we wanted to derive for the weak law of large numbers.